Hey guys, it's your host, it's your host Subhra. Welcome to your favorite channel, Subhra the Geek. So today we are on our fourth video on our mathematics series. So today we'll be talking about complex numbers and how complex numbers impacts in the real world, in the world of machine learning and quantum computing. So guys, as you know, this is a series which I have or a set of series which I have planned along with my very good friend Debayan from industry, who has been working as a core data scientist for a firm for a couple of years now. So we'll be catering to the all the industry needs in our series. So guys, stay tuned for this, and to stay updated, you need to hit the subscribe button and the bell notification icon beside it, so that you get updated each and every time we post a video on our channel. And guys, for any of the problem in during your journey, we have made an exclusive Discord server for you guys. So guys, the link will be in the description box below. So guys, to go join. I and the Debayan will be there to solve each and every query which you throw at us, to the best we can. And we will have a great learning experience from this series. So guys, without further ado, I am your host Subhra, and with me is,
Debayan.
let's start, shall we?
Hi guys, welcome back. So this week we're going to be talking about complex numbers. We're going to try to understand what they are, how they came to be, and whether why should we care about them? Why should we even bother about them? In our learning experience, in our learning journey. So to start off with the idea, right? Let's go back to elementary school. Let's talk about the number line. So if you remember, a number line is just a line. It's a line. It's an infinite, technically a line, which extends to both sides till infinity on both sides. And on the left hand side we have negative infinity, and on the right hand side we have positive infinity, right? And we have our normal numbers, 1, 2, 3, and so on the right hand side of the central point, which we mark as 0. And on the left hand side we have -1, -2, -3, and so on up till negative infinity, right? These are what you would call real numbers. You might have heard of natural numbers, you might have heard about whole numbers, right? They are technically subsets of a much larger set of numbers, which we call as real numbers, and we denote it using this symbol in mathematics. If you're using LaTeX or if you're using MS Word, you will come across this symbol. So real numbers include all fraction numbers, everything that you come in between these numbers as well. So if you have a number around here, let's say 1.5, that comes under this one. If you even divide it up, that's all the decimal numbers, as much precision you can go, they all fall under this set called the real numbers. So where does complex numbers come into play? Where they exist? They don't exist in real life, right? And they are what we call, they have a part, they have a component to them which we call imaginary, right? So the way to represent them is using a vertical plane to this real number, right? Let's shift our whole number line down a bottom, right? And we're gonna have our imaginary number line on top of this as a vertical line, like this, right? So if this is your x-axis, this is a horizontal plane where all the real numbers exist, then this will be your vertical plane. This will be your imaginary vertical plane, where every number is an imaginary number. They don't exist per se. So over here will be I, 2i, 3i. There will be -i, minus 2i minus 3i. And the way we represent imaginary numbers is using this concept of an I or imaginary. We literally call the imaginary number constant as I. And I is equal to square root of -1. This number doesn't exist. It's absurd. You can't have a square root of a negative number because all squares are positive by definition, right? So this is an imaginary number, and all imaginary numbers are represented as a product, as a multiple of this number. So if you're going to write something along the lines of 1.5 imaginary numbers, so you say 1.5i. If you're going to write, let's say, 1.7968 imaginary number, so you're going to say 1.798786i. So every number, every imaginary number on the vertical plane is a multiple of I. That's how the system is developed. Now, now you can see it almost forms an XY plane, right? It forms an XY plane. This plane has a special name. Like when we are working in normal XY plane, we call them a Cartesian plane, right? So you have X, Y, and Z as well over there. We don't have the concept of Z over here, but we do have the concept of a Y axis, which we call, and this real number line and the imaginary number line intersect to form a plane which we called the Argon plane. So this is a special plane, right? And it has its own special name. So how do you represent numbers over here? So let's say we have this y-axis over here. How do we represent imaginary numbers then? We combine them just like you do in a Cartesian plane. So in a Cartesian plane, what you would have is you have the x component over here, you have the y component over here. So if you have a number say 3, 4, that means three times you go in the y-axis, and for 3 units you go in the y-axis, and 4 units you go up in the y direction, right? And together you will have 3 4 34 30 so 3 4, right?
Debayan, could
So
you
in a
zoom on that graph a bit? Because
Mhm.
it's, yeah.
So this is what it looks like. Let me clarify this up. uh, so this part is the horizontal component, this is the vertical component, and this is what we call 4. This is the horizontal component, this is called 3, right? And this one is x, this one is y. This is what you do in a Cartesian system, right? In our Argon plane, we follow the same notion, but the meaning is different, right? So if you're gonna write a number, let's say 3 plus 4i, this is a complex number, right? This means there is a real component 3 and there's an imaginary component 4i. So how do you write this? You write this in the same way like you did in the Cartesian plane. You go 3 times in the x direction, in the horizontal direction. So you stand over here, right? And then in the 4i component, you mark your 4i somewhere over here. So you will have your 4i somewhere along here, 3 comma 4i, right? So this is your imaginary number 3 plus 4i, and using Argon plane you can represent it. You can see that. Please do remember that this plane is the real plane, and the reason why I'm emphasizing that repeatedly is because this is the only one that exists. The vertical plane doesn't exist per se. This is a tool, this is a mathematical formalism which allows us to do great things, like you will see like in a couple of moments. But this is just a tool, and this allows abstract mathematicians and pure mathematicians, purists to be precise, to come up with really good solutions and solve really complicated problems using this domain. You work in the imaginary domain, you solve real world problems. It serves as a toolkit plus, but there are some real world implications of what an imaginary number can or cannot do. Right? We're gonna talk about that later on. First, right before that, we need to talk about something else as well. We need to talk about circles. Now, you might think, where how does circles come into the picture, right? There is a very interesting property which was found by Euler, the great mathematician. Um, as he had done so in many other aspects of mathematics, like he was very proficient in mathematics. So he found a curious representation. He found out that you could represent your number, your imagine your complex number in a pattern of a circular motion, right? And this is what the relationship when compacted looks like. It looks like this. So you have a number e I theta is equal to cos theta plus
Plus
I
I
sine
sin
theta.
theta.
This theorem is called the De Moivre's theorem, right?
Yep.
And this relationship was first found by Euler, later by De Moivre. That's why we have the name on it. And the reason why it's so interesting is because you have the components of a circle, right? These are literally components of a repeating motion. When I say circles, I mean circular motion. I mean anything that goes around in has a revolution, it revolves around something. There's a circular repeating kind of motion to it, right? So you find out that you can represent circular motion, you can represent repeating motion into complex numbers in this fashion, and it's very easy to prove this, right? If you use Taylor expansion, right? If we use Taylor expansion on cos theta and I sine theta, when you add them, you will get the Taylor expansion for ei sine theta. So it's very easy result to prove. But what are the implications? The implications of this are really interesting. And one of the results that we see is something which we call the wagon wheel illusion, right? Subhra will have a picture on the screen for you guys to show, like somewhere over on left hand side. It's really interesting. At first, you will see that the revolution, it's sort of it's going as expected. It's moving fast ahead and ahead. It's increasing in rotations per minute, right? And after a certain moment of time, you will see that it seems as if it's rotating backwards, right? Although it's moving forwards, right? So you will be seeing something along the right. Motion will be going like this. After a certain moment of time, it will seem as if the motion is rotating backwards, right? Now this can be explained using the persistence, like the illusion of eye persistence, that you cannot see a motion beyond a certain frequency at which is the light is captured. But there is also a mathematical formalism to why you see this illusion. This is an imaginary thing, it doesn't exist, but the impact of the effect can be captured by the concept of imaginary numbers. So as you can see, this imaginary number sort of captures this illusion mathematically. So that's your real world sort of insight into how they can make sense. So yeah, one of the other questions that many people sort of come to ask have come to ask is, why do we even bother about imaginary numbers? Like, why did they even come to the picture in the first place? They might argue that it's okay, it's very nice that you have this kind of results from using the imaginary number as a tool, right? But why did it come into place in the first place, right? Like, who thought about it, that I'm gonna use something that doesn't exist to prove that something does, right? It seems so absurd to use. So the idea is, like, there are certain equations that simply not possible to solve in the real world, in the real numbers, right? So have a look at this equation. Would you be able to solve it using any kind of and have a real solution?
I don't think
You
so.
won't. You actually won't, because, like, if you try to solve it, right? So this means that x squared is equal to -1, which is itself absurd, right? If you're talking about real numbers. And this is where mathematicians sort of had a formalism that maybe if we say that there is a number called -1, we can represent all absurd kind of solutions using this as a factor, effectively, like just like we saw here. It's a factor that we multiply with every imaginary number, right? So complex imaginary numbers sort of form the basis of solving equations which are not solvable and in the real world, right? You cannot have a real world solution to them in order to get, in order to have a satisfactory solution to that, right? Now if you have a look at this equation as well, there's a very curious property about this kind of equations which cannot be solved. There is a repeating kind of motion once again about them, right? So if you remember the equation of a circle, right, it looks like, which looks like this, right? They Which looks like this. This thing is the equation of a circle. It almost have some resemblance to this kind of equations, right? And if you look in fact look into the Argon plane, if you look into the diagram, right? If you look at this point, right? If we somehow create a the sort of traces path, right, for places where it has one radius, for example, I'm just making it a very simple example. If we try to keep a one radius of this vector, let's keep this as 1, right? If you try to trace the plot or the loci of this point where the radius will be 1, you will find that there is a circle forming, right? Because the loci is 1, you have a fixed radius, so there will be a circle of that shape. And you will see that some parts of it, like this quarters over here, this part over here, this part over here, this part over here, they all lie, these are imaginary plane, these are imaginary, right? So this is an imaginary circle, and only a very short part of it lies in the real plane. It's almost like cuts in half, right? So this plane, this circle, right, has a very curious equation which Euler discovered, and it's also known as the Euler's identity. It's the equation that ei pi plus 1 is equal to 0, right? This is literally derived from this equation. The insight is that an unit circle will always fulfill this property. So you can see that there is a very strong relationship between repeating kind of circular motions and imaginary numbers, as well as trigonometric functions. And this is in fact called the most beautiful equation in the world, because it brings together the most fundamental constants and the most recognizable constants in mathematics into one simple equation that everyone can understand. It's exponential over here, it's imaginary number. The constant over here, this is pi, or 180 degrees. This is 1. In Boolean algebra, we call this true and false, so that's 1. As well as in Boolean algebra, we call this false. Or in normal digital math, in digital algebra, you will call this 0 and 1, on and off, right? So it brings together all the recognizable constants into one equation, which has a resemblance to a circular or a repeating kind of motion in the Argon plane, which is most likely, like most of it, is imaginary. So you can see it's like you create a tool, you create a way to solve an equation which is cannot be solved using real numbers, and you find out such kind of patterns exist which you never had even seen, and they all sort of fit together as if they were all pieces of a large puzzle that you didn't know existed. It's really fascinating, and that's why complex numbers has been a very interesting subject in mathematics to to learn, and to learn and to talk about, right? Now we're going to go into how this is relevant in machine learning and quantum computing. In machine learning, as per as to my knowledge, there hasn't been much research into this. There has been some papers into this, but there's not much like application of complex numbers into real world machine learning or production machine learning per se. There has been a couple of papers which try to introduce activation functions, as well as those kind of non-linearity functions using complex numbers, but they haven't been much successful. So they still lie on the fringes of machine learning. One prominent one prominent impact of complex numbers in machine learning is in fact in feature extraction, right? In feature extraction, we were going to talking about what feature extraction is in our in a different YouTube series of ours for machine learning. But just to sort of give a very quick description, it's about extracting relevant concepts and ideas from data which AI model can understand and learn from, to then predict when it's being used, right? So for audio, right? So if you have an audio clip, right? You have an audio file and you want to teach an AI model how to understand or read this file and classify it as maybe like human speech. This is the human speaking something, or just like in Alexa, go Siri, Google Assistant, right? Those kind of AI models. They use something called STFT, or short transform Fourier transform, right? Short-term Fourier transform, and short-term Fourier transform exclusively deals with complex numbers, right? What it does, it sort of converts an audio waveform into frequencies, and whenever there is frequencies, there is repeat in motion, right? And when there's repeat in motions, you bet that there will be complex numbers, because you can represent every repeat in motions as a function of cos theta and I sine theta, right? So you might try this out, right? If you use a library in Python called librosa, and if you use the stft function and you pass a audio signal to it, you will get back a matrix where each of the values are complex numbers. It's in this form, a plus ib, and they all represent frequency information. All are circular motions, right? So this is one really a real world application of complex numbers, where we actually come into contact with it during our machine learning life cycle, life process. In quantum computing, they have a more significant role into it, right? And they are basically used in the Schrodinger's equation, right? So just for the just for a quick for people who haven't seen the Schrodinger equation or need a reminder, this is what it looks like. So you have the imaginary number on this side, you have the imaginary right in the front. Bear with me, these are weird symbols, I know, but I'm going to explain them very quickly so that you can understand. Yeah. So this is the imaginary number, right? This is our imaginary number, right? This is Planck's constant, reduced Planck's constant. You can look it up. It's a constant.
Sorry for that, guys. No issues.
Yeah. So and this is a differential. You're taking a differentiation with respect to time,
Time.
right? So this is t is time. So you're taking a differential operator with something. This is called a psi function, right? This is a function, a literal function. Just to find it's a fancy symbol. Don't mind that. It's called psi function, and you have the same term over here as well, right? So what you do is that you can see on the left hand side there is an imaginary number over there. So this whole part, right? This whole part is real. This whole part is also real because the function is a real number function, right? But this thing, the real addition of this thing, makes the whole LHS as imaginary. And on the right hand side, it's all real. So if you put in numbers, if you do normal substitution in just like an equation, right? In Schrodinger's equation, you will find that the left hand side has an imaginary, it's purely imaginary. There is no real part to it. There's no real component to it. On the right hand side, you have a fully real number. So is Schrodinger's equation wrong? Does it mean that an imaginary number can be equal to a real number? That's not true. That's not true. So what it implies is that Schrodinger's equation cannot be solved, or it cannot have real world solutions. It cannot have real number solutions. Obviously, mathematicians would not bat an eye about this, but physicians and physicists would be really confused about this. Like, how would they interpret this in terms of real world phenomenon? Right? Schrodinger's equation formed the basis or kicked off the quantum computing, the quantum mechanics revolution, right? And they form the face of quantum mechanics. How could it? You can show that if quantum mechanics form the basis of reality, how can you show that it's imaginary at the same time, right? So the way that you sort of approach this is that you cannot you sort of work into something called these solutions that Schrodinger's equation gives, right? Schrodinger's are called they give probability clouds, That's the best term I think would help us to understand this. And if you have taken high school, chemistry, or high school stat chemistry classes, you would have come across something called electron clouds, or electron shells in chemistry, right? It's That's what is relevant too, right? Shura will show up a picture on the screen right over here, where he's going to show about the electron clouds of hydrogen, and the way and the various clouds of hydrogen and how they look together. Those pictures that you see, the colorful pictures that you see of the various circles, and how they sort of form different kind of shapes, those shapes are imaginary shapes. Those shapes are defined by the solutions, or the imaginary solutions that you get by solving the Schrodinger's equation, right? And that is what we have observed in real life, that the electron cloud sort of follows those shapes. And you might have come across these shapes too. This is called the S cell, the P cell, the F cell, those kind of shells, right? Orbital shells, right? This is the real world implication of what you're seeing, of our imaginary solution. And electrons exist in those electron probability clouds, using in a probability function of like this. They exist with a probability of the square of the norm of this function, which is called the wave function, right? Using the duality of matter. Like light is also a particle as well as a wave, that concept. So if you represent that as a function called the wave function, and you norm it, that means you take a mod of it, and then you square the number, the result that you will get is directly proportional to the probability that you will find an electron, right, in that cloud. So let's say there is a cloud like this. I believe this is called the px orbital, or something like that. So let's say there is a cloud like this, right? And this is an electron cloud. The electron doesn't technically exist here. It's just a probability shape where the electron can exist, right? And the probability that you will find something over here, or over here, or over here, is equal to this number, right? A sort of proportional to that number, right? And when we talk about in our quantum computing series, you will learn that this probability is what we call the Born probability of quantum computing or quantum mechanics.
So I think that will be all for the day, Debayan.
Yeah.
So guys, thanks to Debayan, we have learned so much about complex numbers and what we really need. There are thousands and thousands of things in the real world that are you can find on YouTube and on many channels, like thousand things to learn on quantum numbers, and you get confused. But we have streamlined them for you and what you need for your machine learning and quantum computing things. So guys, I hope you have liked our video, and if you have liked our video, please give us a like and share it with your friends, though, for those who need it, and to all, so that our video reaches to them properly and they can understand what are the things they need to learn about complex numbers actually. So thanks for staying with us, and as always, we have a Discord server ready for you guys throughout your journey. If you have any problem, you can discuss over there. I and the will be always over there. And if you have any problem, please ping us over there. And guys, if you like this video, please do comment. Please comment anything which you want it as a modification to this series. So thank you for staying with us for so long. I was your host, Subhra, and with me is
Debayan.
signing off. Bye bye.